The objective of this lecture is to provide the first part of the study of non-coplanar impulsive orbital transfer. This lecture focuses on cranking impulse and change in orbital inclination. This lecture is organized as follows. First, a definition is provided of non-coplanar impulsive orbital transfer. Second, the first part of the study of non-coplanar impulsive orbital transfer is developed in the form of what is called a cranking impulse. Now, a cranking impulse is an instantaneous impulse that rotates the orbit plane but does not change the orbital energy. And we'll develop all the conditions for a cranking impulse. After the development of the cranking impulse, the third part of this lecture is to derive the conditions under which the cranking angle is equal to the change in the orbital inclination. Because it turns out that the angle by which the velocity is rotated to rotate the orbit plane is not in general equal to the change in the orbital inclination. But there are conditions under which the cranking angle does lead to an equal change in the orbital inclination. And we'll go through and we'll derive all those conditions. So first, let's define non-coplanar impulsive orbital transfer. So recall impulsive orbital transfer as orbital transfer where the propulsive maneuvers are treated as instantaneous impulses. And an instantaneous impulse is a propulsive maneuver where velocity changes instantaneously. That is, without the passage of time. Now, the first part of the study of orbital transfer was on coplanar impulsive orbital transfer. And in a coplanar impulsive orbital transfer, all impulses were such that the orbit plane did not change during the maneuver. Now, in this part of the study, we are going to start discussing non-coplanar impulsive orbital transfer. And in a non-coplanar impulsive orbital transfer, the orbit plane does change. So impulses can change the orbital plane. Now, the study of non-coplanar impulsive orbital transfer begins with the concept of a cranking impulse. A cranking impulse is defined as follows. Consider a spacecraft moving in an orbit with an inertial velocity VI minus. Now suppose that the velocity VI minus is rotated by an angle theta to a new velocity VI plus. And furthermore, suppose that the change in velocity from VI minus to VI plus occurs instantaneously. So here's what the picture looks like. We have a velocity VI minus. The new velocity is VI plus. The angle between VI minus and VI plus is theta. And as a result of rotating this velocity from VI minus to VI plus, the vector that takes me from VI minus to VI plus is the impulse, which is delta VI. Now, because the velocity VI minus is only rotated to VI plus, we have that the magnitude of VI minus is equal to the magnitude of VI plus. And we're going to call that V. And this is only because it's a pure rotation. There's no change in the magnitude of the velocity. In other words, there's no change in the speed. So as a result, each of these sides, if you want to think of that, of this triangle, have length V. Now, because the magnitude of VI minus is equal to the magnitude of VI plus, that implies the speed does not change. When the cranking impulse, delta VI, is applied. And because the speed doesn't change, that implies that the orbital energy before the impulse, which is equal to v squared over 2 minus mu over r, has to equal the orbital energy after the impulse, because r does not change. When delta VI is applied. So now, given all of this information, we can see that the orbital energy does not change during the application of a cranking impulse, and the goal now is to determine the magnitude of delta VI, which is equivalent to the magnitude delta V, which is the magnitude of delta VI. So now we're going to determine this magnitude of this cranking impulse. So let's rotate the last picture into the form of an isosceles triangle that's a little bit easier to see. So because each of these sides has length v, as I said, this triangle is an isosceles triangle. So suppose we bisect this isosceles triangle vertically, as I've shown. Then each angle, the angle from each of the sides to the bisector, is theta over 2. So this is theta over 2, and the other angle here is also theta over 2. And because this bisector splits the side with the delta V in half, each one of these pieces of that side has magnitude delta V over 2, where delta V is equal to the magnitude of delta VI. So from the geometry, we actually obtain the following result, which is that delta V all divided by 2 divided by V is equal to the sine of theta over 2, because the sine is the opposite side over the hypotenuse. The opposite side is delta V over 2. The hypotenuse is V. So if we solve this equation for delta V, we wind up with delta V is equal to 2V times the sine of theta over 2. This is the magnitude of delta VI. And delta VI is what's called a cranking impulse. And what it does is it rotates the velocity at any point on the orbit. And the angle associated with that orbital crank is what's called the cranking angle. So theta is what's called the cranking angle. Now let's look at this cranking impulse in a little bit more detail. We have that delta V is equal to 2V times the sine of theta over 2. Now, in general, a spacecraft may be moving with a large velocity. So suppose that the speed, v, is large. And also assume that theta is large. Then that implies that delta V will be very large when V and theta are large. So what that means is that if we ask for a very large rotation of the velocity, it's going to require a very large impulse. So that implies a large rotation of the inertial velocity requires a large impulse. And in this case, a large cranking impulse when the spacecraft is moving with a large speed. So in general, a cranking impulse is fairly inefficient. But there's another aspect of a cranking impulse that's also important, is that although this cranking impulse rotates the velocity by an angle theta, the angle theta itself does not actually represent the change in the orbital inclination. So this is very important. The angle theta, in this case that's the cranking angle, is in general not equal to the change in orbital inclination. So, of course, that leads to the following question, and it's an important question to answer, is when is the cranking angle equal to the change in orbital inclination? Now, to answer this question, we're going to actually consider the following scenario. So suppose we have the following two orbits. Orbit 1 is circular with inclination I1 and longitude of ascending node omega 1. Orbit 2 is circular of the same size as orbit 1 with inclination I2 and longitude of ascending node omega 2. So now let h1i equal the specific angular momentum of orbit 1, and let h2i equal the specific angular momentum of orbit 2. Now, because these two orbits are the same size and they're circular, the magnitude of the specific angular momentum of orbit 1 is equal to the magnitude of the specific angular momentum of orbit 2, which will just be defined as h. And also, theta is the angle between h1i and h2i. So now we can see this in the following picture. So here are the two orbits. So the first orbit has a longitude of ascending node omega 1, and its line of nodes is n1. And because it crosses the equatorial plane at the ascending node, the orbit schematically looks like a circle as follows. The second orbit has a longitude of ascending node omega 2, and its line of nodes is n2, and it crosses the orbit plane at its ascending node, and its orbit looks schematically as so. So now, these two angular momenta, which I referred to before, the first angular momentum is h1, and h1 relative to the z direction, which is given by iz, this angle is I1. H2, which can be drawn as so, H2I, the angle between IZ and H2, that angle is I2. And the angle between these two angular momenta is theta, which is the cranking angle. So now we're asking the question, when is theta equal to I2 minus I1? So the question is, when is the cranking angle equal to the change in orbital inclination? Now, in order to be able to see this, we need to decompose each of these angular momenta into their respective x, y, and z components. So in order to decompose these two angular momenta, it's useful to define a new vector, which I'm going to call m, and there are going to be two values of it, m1 and m2. So in each of these diagrams, I'm going to look down on the equatorial plane. So here's ix, here's iy, and then iz is out of the page. Now the line of nodes for the first orbit is n1, and the angle between ix and n1 is omega 1. I'm going to define a new vector. I'm going to call that vector m1. m1 is orthogonal to n1, and it lies in the equatorial plane such that the angle between negative iy and m1 is omega 1. Now, similar to this diagram, I have another diagram for the second orbit. It looks almost exactly the same, and the only difference really is the line of nodes and the vector m. So the line of nodes for the second orbit is n2. The angle that is formed between ix and n2 is omega 2. And similarly, there's a direction m2, which is such that the angle between negative iy and m2 is omega 2. Now you can actually see that if I look at the angular momenta, the two angular momenta look as follows. Here's iz, and here's the direction of h1. And here's the direction of m1. And the angle between iz and h1 is I1. Similarly, if I look at the second orbit, the direction iz is again still up, the second angular momenta is h2, and then the second direction, which is horizontal, is m2, and the angle between IZ and h2 is I2. So therefore, h1I is equal to h times, well, if we decompose h1 into a component along IZ and a component along m1, we get m1, so we've got sine of I1 times m1 plus the cosine of I1 times IZ. Similarly, if we decompose h2I, we get h times the sine of I2 times m2 plus the cosine of I2 times IZ. Now we can also see from the diagrams the following. We have that m1 is equal to minus cosine of omega 1 times IY plus the sine of omega 1 times IX. And similarly, m2 is equal to minus cosine of omega 2 times IY plus the sine of omega 2 times IX, which, if we put these in the correct order, gives us sine of omega 1 IX minus cosine of omega 1 times IY, and m2 is equal to sine of omega 2 times IX minus cosine of omega 2 times IY. So then we can substitute these expressions for m1 and m2 into each of these angular momenta. So then h1I is equal to h times, well, we have sine of I1 times sine of omega 1 IX minus cosine of omega 1 times IY plus cosine of I1 times IZ. And similarly, h2I is equal to h times sine of I2 times sine of omega 2 IX minus cosine of omega 2 times IY plus cosine of I2 times IZ. So therefore, h1I dotted with h2I is equal to h squared times. Now if we look at the calculation, we have sine of I1 sine of I2 times, and we have sine of omega 1 sine of omega 2 plus cosine of omega 1 cosine of omega 2 plus cosine I1 cosine I2. Now, we can simplify this expression as follows, is that we know that sine omega 1 sine omega 2 plus cosine omega 1 cosine omega 2 simplifies to cosine of omega 2 minus omega 1. And then we're left with plus cosine I1 cosine I2. So that's one expression for h1I dotted with h2I. But we can also come up with a second expression for h1I dotted with h2I. So also, h1i dotted with h2i is equal to the magnitude of h1i times the magnitude of h2i times the cosine of the angle between the two vectors, which is theta. But because h1i in magnitude is equal to h2i in magnitude, that's equal to h squared times the cosine of theta. So setting the two expressions for h1i dotted with h2i equal, we obtain the following result. We have that h squared times sine I1 sine I2 times the cosine of omega 2 minus omega 1 plus cosine I1 cosine I2 is equal to h squared times the cosine of theta. So dropping h squared from both sides, we obtain the following. Sine I1 sine I2 times cosine of omega 2 minus omega 1 plus the cosine of I1 cosine of I2 is equal to the cosine of the angle theta. So now, suppose that omega 2 is equal to omega 1. Well, that implies that omega 2 minus omega 1 is equal to 0. And the cosine of 0 is equal to 1. So in that case, we obtain sine I1 sine I2 plus cosine I1 cosine I2 is equal to the cosine of the angle theta, which can further be simplified to cosine I2 minus I1 is equal to the cosine of theta, because sine I1 sine I2 plus cosine I1 cosine I2 is equal to the cosine of I2 minus I1, which then implies that I2 minus I1 is equal to theta. So what we find with this result is, if the two longitudes of the ascending nodes of the two orbits are the same, then the cranking angle is equal to the change in orbital inclination. So we can actually see this feature on the following diagram. So this diagram looks similar to the diagram we drew before, except for this time, the two longitudes of the ascending node are the same. So when we draw this picture, there's only one line of nodes, and it's n, because the two longitudes of the ascending node are the same. So the first orbit has an inclination that corresponds to the first angular momentum, and the second orbit has a larger inclination and corresponds to the second specific angular momentum. And now the angle between these two angular momenta is theta, and the inclinations are I1 and I2. And in this diagram right here, there's only one longitude of the ascending node, because omega 2 is equal to omega 1, which is just equal to omega. And in this diagram, we wind up with theta equals I2 minus I1. Now, the significance of this result is that, and this is what's so important about how to perform an orbit crank, is that the cranking angle theta is equal to the change in orbital inclination only if the orbit crank is performed at the ascending node. If the orbit crank is performed anywhere except for the ascending node, then the cranking angle is not equal to the change in inclination. So if the orbit crank is performed anywhere except at the ascending node, theta is not equal to I2 minus I1. So if you want to actually get the maximum amount of inclination change out of an orbit crank, it must be performed. That orbit crank must be performed at the ascending node, because that maximum amount is going to equal the change in the orbital inclination. And that orbital inclination change only occurs, again, I'll say it again, only when the orbit crank is performed at the ascending node. And that's the key result in this lecture, which is that we've defined a cranking impulse. And as we said, cranking impulses are inefficient because you can see that the size of delta V gets very large if the spacecraft is moving with a very large speed. And in order to be able to get a large inclination change, or something close to an inclination change that's equal to the cranking angle associated with the cranking impulse, the cranking impulse has to be applied at the ascending node. So that takes us to the end of this lecture. So to summarize, first, a non-coplanar impulsive orbit transfer was defined, and it was also put in context with coplanar impulsive orbit transfers. And second, the concept of a cranking impulse was developed. And finally, a key property was derived that the cranking angle is equal to the change in orbital inclination only if the orbit crank is performed at the ascending node. Now, the results of this lecture will be used in future lectures when we continue the study of non-coplanar impulsive orbital transfer, but this lecture will end here.